Welcome to the final module or video of module 1, where we talk about basic linear algebra. And eigenvalues and eigenvectors is probably something you haven't heard in high school. I'm quite certain you haven't, because it requires a lot of math and understanding of what is happening in matrix algebra. An eigenvector and eigenvalues are extremely helpful for you in doing math with matrices, because it turns out matrices can be extremely large and messy, and multiplications therefore can be also quite tedious and calculation intense. And to avoid that, especially if you have to do calculations quite often, we can boil down matrices into eigenvalues and eigenvectors to make it more simple, the calculation. So if we have a matrix A again, and we have a vector x and a scalar of lambda, and it holds that A, the matrix A, multiplied with the vector x is equal to the scalar lambda multiplied with vector x, then the scalar lambda is the eigenvalue of A, and vector x is the eigenvector of lambda. So these specifications, keep them in mind, and what we will be doing here today is we will show you how to get there and walk you through the recipe, which is several steps to follow. It's quite this straightforward procedure once you understand what you're doing and how to do it, but it's also something your computer does for you in a millisecond. So watching this video takes longer than calculate the eigenvalues and eigenvectors of a huge matrix. But again, we need the basics to understand what is actually happening here. So we have some prereqs on the matrix A if we want to calculate eigenvalues and eigenvectors. Again, the matrix must be quadratic. That's a really, really important aspect. The vector x must be in a non-zero vector form, which means that not all elements in that vector can be zero. Sure, some of them may be zero, but it's really, really important that not all of them are zeros, because otherwise you see that the mathematical equation of course holds, but it does not make sense. And eigenvectors can contain non-real numbers. Non-real numbers, this is something you've seen before, other ones with an I perhaps. So you take the square root of -1, and you're like, wait, I learned in high school this is not possible. I should not do that. Well, you shouldn't do that, but mathematically it is possible. And so from that perspective, keep that in mind, that things and results might get extremely messy and not comprehensible for the human mind. But from a mathematical perspective, they are absolutely perfect and fine. And we have this 5-step program to follow. It's a recipe. You walk through it, you get all the eigenvalues and eigenvectors for the n cross n dimension sized matrix A. And if you follow that through, easy peasy, you get there in the end. This is the recipe. Give me a second, I will walk you through the recipe, and then I will show you the recipe, how we will apply that in an example case of a 2 cross 2 matrix. So, in the first step, you take an n cross n identity matrix, I, and multiply it with the scalar lambda. Then you take the identity matrix that you just multiplied with the scalar and subtract that from the matrix A. Then you have another messy equation, messy matrix, and of which you have to take the determinant of the matrix. And then you get some nice statements for lambda, which you solve for that determinant equals 0. Solve that, and voila, you have a beautiful eigenvalues and eigenvectors. Sounds complicated? It is not, at least not in a 2 cross 2 matrix, which we can do by hand. So let's take this matrix A here with the elements -1, 2, 4, and 6. We now have this 2 cross 2 dimensioned matrix. And the identity matrix to that must be 2 cross 2 as well. We multiply that with the scalar lambda, and so we have this matrix lambda I which consists of a lambda of 0, 0, and lambda. Nothing big here. Sounds more complicated and complex in the recipe I just gave you, but this was already step 1. In step 2, you take the original matrix, -1, 2, 4, and 6, and subtract this lambda identity matrix from it. And you see now here that this -1 minus lambda as the first element is already getting a little bit more complicated and complex, but so far nothing big, straightforward math. You learned that in elementary school. You can totally work with that. In step 3, here, this is why I say, like, oh, we do this on a 2×2 matrix. 3×3 calculating the determinant is still possible, but I save you that for your spare time in case you want to do that for fun. And here we have this determinant of this matrix, which is A minus lambda I, and we calculate the determinant of that, which gives you lambda squared minus 5 lambda minus 14. In the 4th step, you just have to solve for lambda if that equation is 0. And that's something you've seen before as well. You know, you can solve that quite easily with the PQ formula, or some of you might be more familiar with the midnight formula. The big fight, which one is the correct way to solve that. It's about the way. The solutions in both cases the same, so pick your pony, and you should end up in this example with lambda 1 as 7 and lambda 2 as -2. So we have 2 eigenvalues now, and one of them is 7 and the other one is -2. To calculate the eigenvectors, we have to do that calculation of the eigenvector for both of those eigenvalues. So in the step 5a here, as I call it, for the first eigenvalues where lambda 1 is 7, we subtract 7 times the identity matrix from A. So we now have -1 minus 7 as the first element. 2 and 4 remains unchanged from the original matrix A that we had. And then we have the element 6 minus 7. Here, really easy math. We can solve this now to the matrix -8, 2, 4, and -1. And here it's getting a little bit tricky, I would say, because we have to set up a homogeneous system where we have this -8, 2, 4, -1 matrix, multiply it with a vector, and that must be gives you 0. So we have the matrix size 2 cross 2, multiplied with a vector 2 cross 1, and have to get that to 0. So, but even that is quite simple, because we know that we can take the first row here, -8 multiplied with v1, so the first element of that vector we're looking at, plus 2 times the second element of the vector, which is v2, must be 0. This is quite simple to solve because v2 equals 4 v1s. And that holds also in the second row. And we therefore know that the eigenvector corresponding to the eigenvalue 7 here is v1, 1, 4. And it's really interesting to see here because you might get different aspects depending on how you solve this homogeneous system, that any non-zero scalar of this vector is also an eigenvector for the matrix A. The same applies for the second eigenvalue that we had, where lambda 2 was -2. We do exactly the same thing. You see now we have a different matrix here. It's the matrix that we have in the first row is 1, 2, 4, and 8. So the homogeneous system that we set up looks a little bit different, but v1 is -2 v2 for both rows, and we therefore get an eigenvector corresponding to the eigenvalue lambda 2 of -2, and the vector is -2, 1. And again here, every non-zero scalar of this vector is an eigenvector for the original matrix. With that, we already have all the mathematical basics that we will need later on when we dive into network theory, which we will use as a basis for input-output modeling. And you have the mathematical concepts. You should understand them, but at no point will you be actually required to apply the math. Because, as I said, your computer is way, way faster in doing that. Perhaps even your phone is faster than doing that than you will ever be, because it's so mathematical calculation intense. But yeah, I hope you enjoyed those introduction in basic linear algebra. I hope it was a good catch-up, and you're ready now to start into digging network theory in the next video.